Hello friends, in this video I will talk about the X-ray diffraction. This method I have used during my PhD to characterize the diamond film. So I will give the more details in the next slides. So concept of X-ray diffraction. So we have heard already during our college time that the diffraction of light. So if we want to see the diffraction of light, that the wavelength should be of the order of the size of the aperture. So this is the condition for the diffraction of the light. Since we know that X-ray is also a wave, so we have the wavelength 1.54 angstrom. So if you want to see the diffraction, then your aperture size should be at the level of angstrom. So crystals and materials can be the suitable for which the interatomic spacing is typically at the level of angstrom. So they are the suitable choice for the to see the diffraction of X-rays. So what happens, we have the incident X-rays, we have the crystal planes which consist of atoms, like you can see the many crystal planes which consist of atoms. We have the incident X-rays, we have the diffracted X-rays. The angle between the two is 2 theta. So we see the diffraction on the detector. So we already know that the diffraction consists of the maxima and minima. So for this you have to check the path difference between the wave coming from the first plane and the next plane. So you can see that the interspacing is d, and the wave coming from the first plane and the second plane has a path difference of 2d sin theta. If you do the simple geometry calculation, you will get 2d sin theta, and the path difference should be of integer multiple of the lambda to see the constructive interference. So constructive interference will give the maximum intensity at the detector, while destructive we already know that is the minima, corresponds to the no intensity, like say 0 intensity. So the constructive interference condition is 2d sin theta is equal to n lambda, and d is what is? D is interplanar spacing, and this is given by a formula 1 over h square by a square plus k square by b square plus c square by l square, where h, k, l is the Miller indices for the crystal planes. So basically that represents many set of planes, parallel set of planes. So if you have x, y, z axis and you have the dimension of the unit cell, let's say a, b, c as the dimension of unit cell, then the intercept on the x-axis is given by a by h, and on the y-axis b by k, and on the z-axis c by l. And n is the order of diffractions. We have always first order diffraction, second order diffraction. So this is the order of diffraction. So constructive interference, what will happen if we have a constructive interference? We will have the maximum intensity, that means we have the maximum photons. So that will give the because we have the photon detectors in the detector, so that will give the maximum number of photons that correspond to the large signal in the detector. While if you have a destructive interference, in that case your intensity will be 0. That means intensity, and that means you have a very low signal, basically noise, detector noise only. So that will serve as the baseline in the spectra. Now XRD applications. So it's a non-invasive method. It doesn't harm anything in the sample. So what X-ray can tell, we also call it XRD. It can tell about the crystal structure of the material. So typical equation is 2d sin theta is equal to n lambda, and if this is the X-ray diffraction of diamond. This is from my thesis, PhD thesis. You can see it, diamond peaks at 43.9 and then 75.3 and then the 91.5. So in the case of diamond, we have the lattice constant, basically 3.567 angstrom, because we know that diamond has a tetrahedral structure. So you can put the since we know that 2d sin in the case of cubic crystals, A equals to B equals to C, So if you see that your formula converter here is a divided by root of h square plus k square plus l square. This is what I use. In the case of diamond, it's cubic, so you have that all the dimensions same. Then you have the formula a divided by h square plus k square plus l square sin theta is equals to n lambda. Let's assume n equals to 1. Then a is constant for diamond. Let's say it's fixed. Then lambda is fixed. The only thing is varied is HKL and theta. So if we get only one peak, that means we have a single theta. That means that corresponds to unique HKL. So we will have only one HKL in the whole sample. So but HKL represents the set of planes. So we have a set of parallel planes. So we have only one HKL. That means if we have a one peak, we have a one set of parallel planes. That means our crystal, the material has a single crystal structure. If you get multiple peaks, that means we have multiple thetas here, and each theta will be corresponds to one HKL. So if you have multiple peaks, you have multiple HKL. So you have multiple set of parallel planes. So in that case, you have a polycrystalline material. And if you don't get any peak, that is amorphous material. So we generally get the X-ray effect in terms of 2 theta versus intensity, which is basically comes from the constructive interference. This is, let's say for example, in this case we got the 2 theta peak around 43.9 in the case of diamond. If you want to see the HKL, what is the HKL corresponds, you can simply use this formula. 2d sin theta is equals to n lambda, and n equals to 1, and theta 2 theta is equals to 43.9, so theta is 21.95 degree. And if you just put in this equation and solve it, then h square plus k square plus l square basically comes out 3. The minimum integer satisfying it HKL is 1 1 1, so that corresponds to the plane 1 1 1. So you can also, if you know the theta, you can also tell the type of the planes, which types of planes is represented in the crystal structure. Now XRD applications again. So if you are doing first time XRD, then you have to check in the literature about the intensity of the sample. Basically this depends on the crystallinity. If the intensity is very high, then it can damage the detector, because and then in that case you have to use the attenuator to get the XRD of the sample. Sometimes you will not get in the peaks in the single crystal material. The reason I will explain here. Since you have the incident X-rays and you have the diffracted X-rays, the angle between the 2 theta, the two angles incident from the normal is equal. You can just see it, incident and diffracted angle are equal. And then with respect to normal, suppose if your planes is tilted, let's say this is not exactly parallel, this is tilted by some angle, and this plane is also tilted by some angle. In that case, your constructive interference will be not exactly at the detector, but somewhere here, that will not give the signal in the detector. So what in that case you have to tilt your sample to make these planes in such a way that it makes the constructive interference on the detector. So sometimes in the single, if you have a single crystal and your planes are tilted, in that case you will not get any peak, because your constructive interference will not form on the detector. In that case you can do high resolution XRD, which basically tilts the sample and find out the crystallinity of the material, whether it's single crystal or not. If it is a single crystal, you will see the peak in the high resolution XRD. You can also estimate the crystallized size using the Serrer formula, which uses basically peak information, a peak to FWHM, to estimate the crystal size. And you can also do high resolution XRD. This can also tell the defects or dislocation density in the material. For this you can use the omega or omega 2 theta scan. I give the link below. If you want to read it, how to do it, you can read it. Once you have the XRD pattern, you can plot it using Expert Plus or Expert High Score Plus, which is a plotting software which allows multiple operations on the peaks, like removal of the K alpha peak or smoothing of the peaks. These all operations on the peaks you can easily do in this software, basically made for the X-ray diffraction. And finally, once you have everything corrected, you can plot the final spectra in the Origin Pro software, and that we normally put in the research paper. And if you want to know the peaks correspond to your sample, you can use also JCPDF database. This is also a software to get the information about the peaks in the material. So this is all the information about the XRD. Okay, thank you.